Okay, let's keep on going with the homework. Number 4, the part 1, and it's number 13. Indicate whether energy is emitted or absorbed when the following electron transitions occur in hydrogen. Electron energies are quantized within the hydrogen atom. The electron may have only discrete energies as represented by the principal quantum numbers. Okay, so yeah, there's energy level 2 to 4. The higher the principal quantum number, the greater the energy. So that means that if it's going from a lower energy level to a higher energy level, it's absorbing energy. If it's going from a higher energy level to a lower, it's emitting energy. So if an electron is promoted from a lower to a higher energy level, a quantity of energy must be absorbed. So in each one, just look which is the higher energy level, and it's starting here. For example, number A, let's just do number A and number E. N equal to 2, N equal to 2, 2 and 4. So where is going from to a higher energy level, from a lower one to a higher. So that means that it's absorbing. Energy is being absorbed. Now E, letter E, ionization of an electron in the N state. Ionization energy, remember, is the energy required, so energy is absorbed. Energy is absorbed. Now, ionization of an electron in the N equal to 2 means that the energy is going to an infinite. Why? Because you are taking off that electron from the orbital. So that means that it's going from to an infinite, N equal infinite. So yes, it is an increase. It is energy absorbed, but the most important thing is that you can understand that from energy N equal 2 to N equal infinite. That's how that's the transition of the electron. And why is it called infinite? Well, because it's so further away from the nucleus that it's an energy level infinite. As you can put 20,000, 100. Let me move this a little bit up, and let's do number 14. So using the modified Bohr equation for the hydrogen atom, remember which one is the modified equation? It's this one, okay, on the energy level T to F. And it says, calculate the energy of a photon emitted for each of the following transitions. N4 to N3, N3 to N2, and N2 to N1. Take note of the magnitude of energy difference between adjacent level as N increase. Okay, so let's go ahead and do letter A. So when you get here, let's do two of them. Okay, so that way we can just take note of the magnitude of the energy difference between adjacent levels as N increase. That means that N equal to 4 to N equal to 3. Those are adjacent levels. And let's study to be able to compare them. What's going to happen with the energy between N and 4 when the electron goes from 4 down to a 3 level, or from N equal to 1 to N equal to 2? n equal to 2, to 1/2. So let's plug in the values of n on the Bohr, modified Bohr equation for the hydrogen atom. And it's the energy, the difference in energy, and let's just from the 4 to the 3, okay, would be from the energy level 4 to 3 would be 1, if you remember the equation, this is the constant, by 10 to the minus 18 multiplied by 1 over, that was the equation, initial minus final. And this would be the initial. Let me write the equation here. The difference in energy from the n initial to the final energy level will be equal to 2.18 by 10 to the minus 18 multiplied by 1 over the initial to the square minus 1 over the final to the square, and this is joules. Okay, so 1 over, let's plug in the values. What's the initial? That's going from 4 to 3, so here would be 4 to the square minus 1 over 3 to the square. Now notice that as it is emitting, it should be emitting energy. Why? Because it's going to a higher state, which was the electron was, let's say it this way, was taken to this stage by applying energy, absorbing energy. The electron absorbed energy, went to a higher energy level, and then went down as soon as when that source of energy was taken away. So it went down to its lower energy state. So when you get this value, let's plug it in, let's calculate it, and it's 4 to 3 gives you 1 over 16, 1 over 9, and that value is minus, of course, emitting energy, 106 by 10 to the minus 19 joules. Now, what is the value for energy level from 2 to 1? Is equal, again, 2.18 by 10 to the minus 18 joules multiplied by 1 over 2, because that's the initial state, to the square minus 1 over 1 to the square joules. And that gives you that the difference between 2 and 1 would be equal to minus 1.634 by 10 to the minus 18 joules. Now I did this 2 to the extreme. You can do from N3 to N2, that is the middle value, the middle energy level. So if you go 4 to 3, 3 to 2, and 2 to 1, you will see with more detail when I'm got the trend of the energy level, the release of energy. And basically the trend is when you go to a higher energy level, the difference between the energy, like for example, if the electron is in an energy level 4 and goes down back to an energy level 3, the difference in the energy, or the energy emitted, is minus 106 by 10 to the minus 19. Now look at the 2 to 1. The energy increases with lower energy level, and that's the trend. Let's go ahead and do letter B now. And letter B is basically, let me move this down and get the problem, and it's calculate the wavelength of each of the photons above and classify with respect to the region of the electromagnetic spectrum what do you have to do? You just have to calculate with the energy the wavelength of each of this energy. Remember, this is the energy per photon, okay? So what you have to do here is you have to, after you got the energy level, what you have to do is just plug in the values of speed of light and Planck constant, right? And then you find out the wavelength. Let me do the first one, okay? Let's do it with the energy level 4 to 3, and you'll see what I was explaining. You will understand what I was explaining. Energy level from 4 to 3, right, is gonna be minus 1.06 by 10 to the minus 19 joules. Now, if you got that the energy, Planck energy of a photon, and this is supposed to be the energy of a photon, okay, and of an electron photon, and minimum particle, minimum amount of energy. Remember, the minimum amount of energy is the energy levels of the electron, and that's why it's called quantum numbers. And then you got the energy of a photon would be the Planck constant multiplied by the frequency. And as I told you that if we can plug in directly the wavelength, it would be the speed of light, right? Speed of light multiplied by wavelength by frequency. Now, frequency would be equal to speed of light divided by wavelength. Just to plug in this frequency here. So the energy of a photon would be equal to h, Planck constant, multiplied by speed of light divided by wavelength. What are they asking for? They're asking for the wavelength. So they're asking you for the wavelength. And what region of the electromagnetic spectrum is. So let's go ahead and look at the photon emitted when it goes from, the electron goes from an energy level 4 to the 3. And so we plug it in, and by the way, if you got a negative sign, it doesn't matter because this energy is the absolute value. So when you got here, you can plug in 1.06, doesn't matter, by 10 to the minus 19 would be Planck multiply. What is the Planck constant? 635, 630, 6.63. That's the value. 6.63 by 10 to the minus 34. Okay, joules multiplied by second by, multiplied by 3.00 by 10 to the 8 meter per second. Okay, and divided by wavelength. You don't got wavelength, that's what we're trying to find out. So if you go ahead and plug it and find out wavelength by multiplying both sides by wavelength and divided by 1.06 by 10 to the minus 19. As you know already, the negative sign here is just telling you that this is emitted energy. But you can just omit this sign when you're doing the calculation of wavelength. You cannot have a negative wavelength. But it's because this is just telling you that. So let's take out that sign now. And it's 6.63 by 10 to the minus 34 joules. We already got rid of the seconds. Multiplying, and this is joules, by the way, and multiply by 3.00 by 10 to the 8th meter. We already got rid of the seconds, and this is divided by 1.06 by 10 to the minus 19 joules. And that gives you a wavelength of, we're doing 4 to 3, right? Gives you you just can double check my calculation, 188 by 10 to the minus 6 meters. And this is infrared. Just look at what you can do is after you obtain this value, just look at the tables on your book and the literature. So now let's go to number 50. And you have to do it, by the way, you have to do it with all of them. You have to do it with the energy of the energy level from 3 to 2 and 2 to 1. You just complete it to practice it. Okay, let's go ahead and look at this. Calculate the energy required to ionize a hydrogen atom in ground state. Well, what did I say? I said that the hydrogen, how I said before, what is happening here? A hydrogen gas, right, plus the energy of a photon, hydrogen plus gas plus 1 electron. Hydrogen lost 1 electron, right? And that means that the electron is infinite, what I said. When you lose an electron, it's going from the energy level, ground state energy level, to infinite and equal infinite. But what is the ground state electron configuration of the hydrogen? Let's look at it for a second. And it's H1S1. And it's N equal to 1. It's the lowest energy possible. So what are we calculating? We're calculating the delta energy of a photon from 1 to infinite, because that's the concept of ionization energy, and it's 2 by 10 to the 18 by 10 to the minus 18, and it's 1 over 1 to the square minus 1, that's infinite, square, and infinite, 1 over infinite is 0, if you remember that from math, right? So if this is 0 and this is joules, this is 2 by 18 by 10 to the minus 18 joules. That's the energy of ionization energy. And the second question, the lithium plus 2 ion has only 1 electron. Would you expect the ionization energy of lithium plus 2 to be larger or smaller than that for hydrogen? Explain. And basically you have to base your explanation is that lithium plus 2 is 1 electron system with 3 protons in the nucleus. So what do you think is going to happen? It's a higher energy level because you're taking an electron, the only electron left, in which you have 3 protons in nucleus. It's going to pull it harder. So it's going to require more energy to pull it out. And that's the reason. Don't forget the reason, more energy. And let's finally look at number 16, and it's the Broglie wavelength. Remember, Broglie, what put together was the behavior of an electron as a particle, the particle and wave character of an electron. And I explained that in your lecture, and I was explaining the standing wave, and that the electron behaves like a standing wave, and that I explained also the interference, and when both of them had the same frequency, it would be double the resulting wavelength. So according to the Broglie, matter in motion is described as having both particles and wave character. The wave character component increases as the quantity of mass decreases, and or the velocity of the mass increases. And that comes along with the uncertainty principle too. With very small mass, you cannot exactly predict where the position of the electron, the momentum. So letter A, what is the wavelength of a grain of sand that has a mass of 234,500 grams and is moving at a speed of 0.0100 meter per second? By the way, 1 joule, don't forget that it says it here, is 1 kilograms multiplied by square meters divided by square seconds. And then it says, what is the wavelength? Okay, and so using what we need to do is use the Broglie's formula. You will be given these formulas. So the Broglie wavelength formula is the wavelength would be equal to the Planck constant divided by the mass multiplied by velocity. But be careful, this is velocity, not frequency. That's why when I write frequency, I write it like that, because this is frequency, right? And V will be velocity. Okay? So if you have any particle moving, this is not moving at the speed of light. It's telling you the velocity already. Okay? So it's asking you for the wavelength. And h would be the Planck constant again, 6.63 by 10 to the minus 34 joules per second divided, what is the mass is, by the way, we're going to convert it as joules is given in kilograms multiplied by squared, the meter per second. Let's go ahead and convert this to kilograms. And you know that 1 kilograms is 1,000 grams. So if you get 0.000100 grams, desired unit would be on top, kilograms. Given unit is on bottom, 1,000 grams. So grams and grams cancel out. So this, I'm going to do it on top, would be 1, 2, 3, 4, 5, 6, 7, 8. And 1 by 10 to the minus 8 kilograms. So let's plug it in here, down, and it would be 1 by 10 to the minus 8. Just double check my calculation, please. Kilograms multiply, yes, that, by the velocity, and this would be 1 by 10 to the minus 2 meter per second. Now, if you got this, it's going to give you, right, wavelength would be given in joules. But let's go ahead and instead of using joules, let's plug in this value so we can get rid of the kilograms. And what are we trying to accomplish? We're trying, wavelength is given in meters or nanometers or centimeter. We want to accomplish those length units. And it's going to be, making all this calculation, this is going to be, let me erase it here, right? Okay, and this is gonna be, joules we know is kilograms multiplied by now if you got this, kilograms and kilograms cancels out. This seconds cancels out, and 1 meter cancels out with meter, and you got meter on top. And this is going to give you 6.63 by 10 to the minus 24 meter. Okay, now let's go ahead. As you see, it's a very small wavelength. Now let's go ahead and look at letter B. And letter B says, right, what is the wavelength associated with an electron traveling at 1/10 of the velocity of the light? Oh, it gives you the mass of an electron that we know already is 9.11 by 10 to the minus 28 grams. The mass of an electron is 9.11 by 10 to the minus 28 kilograms. And to take it to kilograms, again, we divide it by 1,000, and it's going to be 9.11 by 10 to the minus 31 kilograms. And this is going to give you, again, the same thing, but there's a difference here, and the difference is that an electron, right, it says that the electron, here it is on top, is traveling at 1/10 of the velocity of the light. 1/10 of the velocity of the light. What is the speed of light? 3 by 10 to the 8 meter per second. So what would be 1/10? The velocity of this electron would be equal to 3, of course this is 3.00, 3.00 by 10 to the 8 divided by 10 meter per second. So it's going to be velocity of this electron 3.00 by 10 to the 7th meter per second. So you're going to go ahead and you're going to have here that the wavelength would be, then you plug it in again like we did, 6.63 by 10 to the minus 34. And instead of joules, let's plug in kilograms, multiply by meters to the square, divided in seconds, right? And this is the units of 663 multiplied by seconds, right? And this is, and by the way, this is like that here. I made a mistake here, sorry for that. And this is because this is meter square second, and this is the joule multiplied by second. Now we got it better. Okay, so this second and this doesn't cancel out, and with this one too. So here the same thing. This cancels out with this, and then you got on bottom. What is the value on bottom? It would be the mass of the electron, which is 9.11 by 10, and we already converted to kilogram, minus 31 kilograms, multiplied by the speed of light, 1/10 the velocity, which is 1/10 the speed of light, to the 7 meter per second. So the last second cancels out, kilogram and kilogram, and then you get the results. And this is it for this homework, the part 1. In a little bit, we'll start part 2. I will record another video, and we'll get to finish all